Okay, we're going to go through the multiple choice section of the induction test now. I'll go through a few questions at a time. I expect you to pause and read the question properly. I'm just going to absolutely blap through them. So we have got, oh hello, what's going on? 65 nucleons, 28 protons. It's a beta minus, so plus proton, so that's a neutron going to a proton. So whilst this 65 stays the same, we have got a neutron turning into a proton, so we know that it's going to be 29 protons. So it's one of these two answers. But you know what, I'm not even going to work it out, because this says number of neutrons. Well, 65 is the number of nucleons, so I don't need to work out the number of neutrons because it's not 65, so it must be 36, so it must be C, which is right. It's fortunate. Right, let's move on to the next question. Question 24. I'll let you pause to read it. Okie dokie, phase difference of standing waves. If I've got a standing wave like this and I draw it as a loop diagram, everything within this loop is in phase, everything with this loop is pi out of phase, and everything in this loop is in phase of any point on this loop. So I'll just be clear. If I've got X and Y, they're in phase. If I've got A and B are in phase with each other, but they're pi out of phase with X and Y. So the actual question is, what's the phase difference between P and Q? Well, they are on the same loop, so they are in phase, so the phase difference is 0. Bosh, A, everybody's happy. Just realised I've snipped this from my screen. It's a smidge fuzzy, but hopefully it's clear enough. Right, let's have a little look. What do we know? Lambda equals 5 times by 10 to the minus 7. It's n equals 4. We're using n lambda equals d sine theta because that's the diffraction grating. We know that's 30. What is the number of lines per millimetre on the diffraction grating, which fortunately is what is shown from this, because it's not the distance between the lines, so that's fine. Let me just double check we're okay with that. No, I'm being an idiot. That's D is of course the distance between the lines. So that's, if I've got all these diffraction gratings, that's D there. So I need to convert that. So 1 over D equals 1 over n equals D. Oh, stupid thing. Equals D. Where that's the lines, and we need to be careful, that's lines per millimetre, we need that in per metre. So there's a few things to do there. But let's get D and then we'll convert it afterwards, because we're not having to use these values, so that's not the end of the world at the moment. We can convert that right at the end. It shouldn't be an issue. So, what have we got? We've got 4 times 5 times by 10 to the 7 over a half. Well, that's going to be 20 times by 2, that's going to be 40. 40 times by 10 to the 7. And that's in meters. So that equals D. Get that back. So that equals that's D equals that. So we need to do 1 over D, well, 1/4 is going to be a quarter, so I know it's going to be one of these two. It's not going to be C or D, so we just need to get our powers of 10 sorted out, don't we? So equals 1/40 times by 10 to the -7, and this would now be in meters to the -1. So I'll just chuck that into my calculator. Just remember that Maths very kindly gave me one of their on-screen calculator licenses. So that's 250,000. That's in per meters. So to get it in per millimeters, we need to divide by 1,000. And I make that 250, which is the same as that. Whoops, which is the same as that, which is in fact the answer. Okay, so we want to work out the moments of this. So that's what we're actually after, isn't it? That force there, the weight of the object. No, that's an absolute lie. That's the force we want. That's the weight we want. This is 2.5, lovely. And we know that the weight of the ruler is 1.5. And that is sitting, for the sake of argument, we'll put it there, and we'll say that that is 50, 50, because it is. So we could easily work that out from the pivot. 50 minus 15 is 35, so leave that like that. And how much is that? It's 1.5 newtons. So our two clockwise moments are 2.5 times 60 and 35 times by 1.5. Add those two together. I thought that was the mass of the pan. Yeah, what we'll do is we'll just take that off at the end. Let's just take that off at the end. Okay, so those clockwise moments are 202.5. So the anti-clockwise moments also equal that. So it's 202.5 and it's divided by 15, so let's just do 15. It doesn't matter, we're keeping it all in centimetres, it's irrelevant. We're just doing that. So divide that by 15. Bosh. 13.5. We'll nip off that 0.5 now. And hopefully one of the answers is 13. Which it is, and that's the right answer. If you got 13.5, you can have a moral point, but sadly not a real one, because you've done all the hard work, but you've forgotten to take off the weight of the pan. Okay, so the classic ball dropping question. We've got two balls, they're 25 centimetres apart. This one is dropped vertically like that. This one has got a horizontal projection of 0.1 meters per second, well that's 10 centimeters a second -1. It's 1 second and it's going towards it. So this will go at a path like this. They're going to drop at the same rate, so it's only the horizontal that we're interested in. We don't care about the vertical at all, completely irrelevant. So that's 10 centimeters, so that's going to be after 1 second, that's going to be 15 centimeters, which is the same as A, which is the answer.